So what I want to do is go into a little bit of the math first, and then we'll jump back to a video actually for a little while as well. I'm trying to find the best way to do this distance learning, and I find that like writing only is going to get boring right away, so I'm trying to like mix it up a little bit. So really what we're focusing on is 10.5 right here. And then we'll get into 10.6, 10.7, and 10.8 kind of as one topic because they're very much related to each other. So the beginning of 10.5 tells us that I, the moment of inertia, if you recall from 10.4, was really the summation of m sub I times r sub I squared. And this was from 10.4 when we looked at the rotational kinetic energy. And we said that rotational kinetic energy was 1/2 I omega squared. This was how that formula was analogous to kinetic energy from translational kinetic energy. So this is the definition of I, but this is only good when we have all particles. So if I've got a rod and there's particles some places along the way, and that's rotating about the axis, which is, say, my hand, then as a result, what will happen is those particles themselves will be like the mass concentrations in those locations. But if I have just simply a rod without masses along the way, then the mass of the rod is like a continuum. Its mass is distributed throughout the entire length. By the way, can you guys see me as well? Do you all know how to split the screen when it's screen sharing? Because if you don't know how to, there's a way to do it. So make sure you can see what I'm doing with my hands also. That's why I'm trying to be a little animated here. Okay. So that's the general formula that we start with when it's particles. But when it's not particles, the formula for I becomes an integral. And we integrate r squared dm. R squared dm. Now, r squared, again here, is r is the distance from the rotating axis, and that's the same, it hasn't changed at all, right, from here to here. But when the mass is concentrated, we can literally find the I value by adding together all of those masses from the center. But when the mass is not concentrated at one location or several locations, yet it's distributed, we have to look at the mass, and we have to look at little infinitesimally small parts of the mass, dm's, little pieces of it, kind of like dx and dy like you've seen. Now, what I'd like to do is just go through a couple different shapes so you guys can get an idea of the shapes and what they look like as far as their I values, and then we'll derive a couple of different examples. So I'm going to go to the next slide to show this, so give me a moment. And I'm going to take a quick picture of this so you guys can see it. So I'm on page 274, what I'm talking about right now. Let me just quickly crop this, guys. Hang on. Okay, perfect. So what we're noticing, say again? It's the integral of r squared dm, where r is the distance from the rotating axis, and dm is a small piece of the mass along the object. So these formulas here we're looking at are for different objects in different scenarios. So the first one that we're looking at there is the hoop about a central axis. So we're looking at something that doesn't really have much length to it. Notice there's no L value. Whereas if you look at the one directly below it, the solid cylinder, let me point so you guys can see this. The solid cylinder, the length matters, and it's rotating around this axis now. It's not rotating around that axis. So notice when it's rotating around this axis, let's see, this is the axis right here. These are the exact same shapes. When it's rotating around this axis, the length doesn't affect it at all. It's just the R value because the mass is distributed at some distance from the rotated axis. The length is not affecting that though. While in this case, the length and the radius both matter because the further away in length, the further it is from that axis as well. Again, this axis is up and down. So the axis location is probably the most important thing that we're going to be focused on, the location of the axis itself. Now, what you'll notice is some of them are fractions with mr squared and ml squared. Some are just ml squared, like a really, really thin rod where the radius is negligible. Like look at these two. They look identical, right? But this is a really thin rod where the R value is so small that it doesn't matter. So this becomes such a small number that when you go to use your formula here, this becomes practically 0, which is what's giving you this right here. So you're just dropping this piece off to give you the 1/12 ml squared for the second one here. Now again here, because it's rotating around this axis, the length does not affect it because it's how far the distance from the rotating axis is, which is the radius. This one has to do with a ring that has some thickness to it, right? This is a hoop, and this is what they call an annular cylinder, a ring. So these are identical, really, when you look at them, but this one is not very thick. It doesn't have a wall thickness to it. So this is a very slender hoop, like a hula hoop almost. Whereas this one is more like a washer, okay, a washer spinning around something and has some thickness to it. Now, notice again the formulas differ slightly. After these 5 or so, we get into spherical objects. So we first have a solid sphere, 2/5 mr squared, and then notice, look, a thin spherical shell, 2/3 mr squared. Why is this one a larger value than this one was over here? What's the rationale behind that? And think about what I is really a measurement of, what we said, how I changes. What do you think? Yeah, the mass is concentrated further away when it's a shell. Imagine this being hollow, right? So if the mass is all pretty much on the outside here, then you're going to have a larger R value. And if we think about our formula for I is I equals R squared dm. So the R value being greater because the mass is all concentrated on the outside is what yields a larger I value for a hollow sphere versus a solid sphere in the other scenario. So if we look at this next one here, we've got a hoop about a diameter. So this looks identical to this one, right? If we look at these two, but the major difference here is that this is rotating about a different axis now. Right? Look at this axis versus this axis, and it clearly changes our result. We have half the rotational inertia than we did earlier because a lot of this mass is very close to the axis. Like, look, I'm thinking about this object as a bunch of little masses put together. See all the dots I'm kind of making here? Okay, all of these masses that are really close to the axis don't contribute much because their R value is so small. So when this thing is rotating, the mass right here is not having much of an effect on I. But the mass here is having a large effect on the I value. So because some of the mass is close and only part of it is a further distance away, this number is going to be less than this one, where in this case, all of the mass is a far distance away. None of the mass is concentrated around the axis. So these two compared to each other, we can see why this one is greater than this one is. And then finally, the last one is a slab. And this is a slab of a piece of a solid here, okay, with a dimension A and B here. And that's just the derived formula for it. So now what I want to do is I want to pause and go over a quick derivation of this before we get into what's called the parallel axis theorem, which is on the bottom of page 274. That's kind of what we're going to go to next. Matt, go ahead. So that's a good question, Matt. So the only time an L value is going to play a role is when we have an additional parameter, not just the radius. So if you look at this, the radius from the center outward is the same no matter where I look at it, right? This is the radius. I keep pointing to all these. So there is no length in this case. If this had some, say you extruded it into the third dimension, if this hoop went in this direction like that, Matt, then you would be in a scenario very much like this one right here, where this has a radius, so we know that the mass is separated from the axis slightly because it's a further distance away. But then, look, here's the axis. Some of the mass is at the very end. So the length of this one matters because it's a distance away from the axis where it's rotating, whereas this one isn't in that case. So it's when you have a second dimension of your mass concentration that pulls it either further away or closer to that rotating axis. Sorry, I'm laughing at Londell's background. Matt, does that make sense? Does that make sense why in this case it doesn't have it? Because we don't have a length to the hoop. The hoop is just one value. So what you're visualizing, Matt, is this hoop, or really this cylinder, if it were pretty much hollowed out. If this cylinder were hollowed out, it would be this hoop right here, right? With a dimension in this direction. And then L would be included in the formula here at the bottom. Okay, the good part about the exam is that a lot of these you're going to utilize and not have to derive, but you have to kind of still understand why some are different than others, okay? And that's why I did that little, I showed that little video of the things rolling down the ramp so you can see that concentration idea of the mass being on the outside. Okay, I'm going to stop screen. We copy that, yeah, from this table right here we're looking at now. So let me just think about this. So which of these we're looking at in this case? Well, these look very similar, right? This looks similar to this, which looks similar to this. So we're really in one of these three scenarios here. Does everybody see the three scenarios I'm pointing to right now? So when it says a solid cylinder, obviously I know the word is there and the word is there. This is different because it's a thin rod. And notice, what does the thin rod not take into account? The radius. See how the radius is involved here and the radius is involved here? Yet on this spot, the radius is not involved because the thinness of the rod is what makes R pretty much 0. That's what's happening here. So this setting is like having the radius, but the radius gets smaller and smaller and smaller. So there's no radius involved in this one because, again, the radius is negligible. It's very, very thin. It's like a piece of spaghetti. Think of this as a piece of spaghetti, and think of this as like a can of soup. So we're looking at a can of soup. So we're looking either here or here. It's one of these two options. It's either a solid cylinder about its central diameter or a solid cylinder about its central axis. So we have to ask ourselves which one of them is it for our case. So let's think about these. So the parallel axis theorem, we're going to finish with this idea real quick. I know we have a couple minutes left. The parallel axis theorem is the idea that what if we're not rotating about the center of mass? How does it work is the question. And that we can prove with the one that we started with a moment ago where we rotated about the end of the rod. And the idea behind this is that the rotational inertia is going to be the same as the rotational inertia around the center of mass plus mh squared. Now, here's the key. Here's the rod. Let's draw this rod here. And let's assume we know the rotational inertia about the center of mass, which is right there. And the rotational inertia about the center of mass of a rod, we just said, was 1/12 ml squared. So that value is given. So we can go ahead and write that as 1/12 ml squared. But then what we have to do is we have to think about how far is the new axis that we're going to rotate about. So let's say we're rotating about the end of this rod instead of the center. Put the axis of rotation here now. This is defined as h, the distance between the parallel axes. So this one is a distance of L over 2 away. So this becomes m times L over 2. Remember, the length of the rod is L. That's L up there. So it becomes m times L over 2 squared. And then if I simplify this, I'm going to get L squared over 4. And L squared over 4 in terms of 12 is going to be 3L squared over 12. And then we have here, if we look at this, we'll have 1/12 and 3/12, so give us 4/12 ml squared, which is really ml squared over 3. And that's what we derived a little while ago in the first part, or what the author derived, I should say, in the first part of that last video. So the parallel axis theorem, is introduced in your text in this section, in section 10.5. So it would be useful to look at that. Now, I like the way the author describes the parallel axis theorem and goes through a whole derivation of it at the end of this video. So what I'll do is this. I'm going to put a link to the video that we just had up a moment ago, and he's going to do some other derivations, and then I'll skip ahead to the parallel axis theorem. So what you guys should do is you should watch, like, it's about 2 minutes, 2.5 minutes of that video. And then over break, please look to see if I assign an Edpuzzle video or two. Okay, I might just assign a couple just as just a means of review for the AP exam so that you guys could watch some older stuff like kinematics from earlier this year and just get an idea of how it's going. I'm going to try to use the Flippin' Physics channel because that author, I think, does a really good job of describing what you need to know for the exam specifically, and does a good job of interacting with those fake students he creates so you kind of see what other students would think as they're going through it. Okay, it was a lot we took on today. This is not an easy topic, okay? This is 10.5 of our textbook. We are going to look at 10, and we really did look at 10.6 because it was torque, but we'll look at 10.6, 10.7, 10.8, and we'll do some more example problems of this in our next meeting. So plan on our next meeting being in class, but if it's not, it'll be on the Tuesday after break, and we'll do that virtually again, and we'll do probably more examples this time of 10.6 through 10.8. Okay, I'll probably assign you a couple of problems for homework for 10.5. I haven't looked at it yet for homeworks, but I'll try to give you an idea of that. You guys all have class to go to. Sorry, I know. Let me know if you have any questions. If you hang around and ask me some questions, you can hang around on the video. I won't leave until everybody else does. If I don't see you guys, have a good break for 2 weeks, and I will see you obviously when you get back. You're welcome, guys. Notes. Go back to let me see where that table is for this problem. Do I have it in the pre-problem? Okay, so back in the problem now we're here and we're seeing it says that this is rotating about an axis perpendicular to the cylinder. So let's start by drawing the cylinder if we need to mentally. Okay, so there's our cylinder. And it says it's rotating about an axis perpendicular to the cylinder. Perpendicular to the cylinder. And it's located 2.3 meters from the center of mass. Well, the first part is that we have to recognize if we're giving no information about the cylinder and its uniformity, we assume it's uniform. If it says, you know, that the cylinder is one material on one half, another material on the other half, then we have to break it into two parts with two different masses and figure that part out. But in this case, here's the center of mass right there for sure. Okay, and here's the center of mass along its rotational axis for sure. So those are both considered center of masses. The question is really, which way are we rotating? Are we rotating it like this, around that axis? Or are we rotating it like this, around the blue axis? So which axis are we rotating it about this time? And again, I know this axis will be slid away because it's 2.3 meters away from its center of mass. But which of those axes, or which of those rotational models are we going? The red one, which is along that, or the blue one, which is this way? Good, the blue one, yeah. And again, we know that because of the word perpendicular. The key is the word perpendicular. It's perpendicular to the cylinder, and we can see here that we've got a right angle right there. So there's the perpendicular constraint. Thank you. So the perpendicular nature shows us that this is going to spin along that blue direction. Now, the axis that we're rotating about, we don't know how long this solid cylinder is, or do we? I'll have to give you some information about that, so I'll add that piece in a moment. But we know that the rotational axis that we're looking at, I'll draw it in green, is somewhere away from the center. And we know that this distance here is 2.3 meters. So right off the bat, we can start by listing some givens. We're told that the mass of the cylinder, we'll call that M, is 4.5 kilograms. And we're told that the distance from the center of mass is 2.3 meters. So I'd definitely have to give you more information for you to solve this. So what other information would the problem, what would be necessary for this problem based on the formula from the table that we're looking at there? What other information do we need? And I made up this problem, so it's not like the book forgot information. I just didn't include it. What are the two pieces? There's two more pieces of info that we still need to help us to solve for a problem like this. What are they? Carrie, go ahead. I see your hand up. So the radius and then the length, that's a good question, right? The length we have to consider. So what we have is h, and h is the distance between the center of mass and the rotating axis. So we don't have the length right now. So yes, we would need the radius and length. So let's assume that those were given information. So based on the physical nature of my drawing, I'm going to call the length 2 meters. I'm going to say the length is 2 meters. So this would be given in the problem. So I'm going to put it right here. And the radius, we'll say, is going to be 0.5 meters. Okay, so again, those things would have to be given in the problem. They would have to be given in the beginning of the problem or at some point in the problem. Now, with that given information, we can then calculate the rotational inertia of this rod. And what we do is we recognize that because we're not rotating about the center of mass, but instead we're rotating about that green line, we have to use the parallel axis theorem. And that tells me again, what is it, mh squared? Okay, so we have to look back and say, what is ICOM? What is the rotational inertia about the center of mass? And that's given in the table. Again, I do not recommend that you memorize these. Do not memorize the center of the rotational inertias. Simply plug them into your calculator, or they'll be given in some problems too. If it's a really complicated setup, they're given sometimes. It'll say the rotational inertia of this body is, 1/7 mr squared, and it's this weird amorphic looking shape. So they've done the integration for you. Now, when it comes to a thin rod about its center of mass, or a disk about its center, you want to memorize those. You want to, have them in your calculator, not memorize, have them logged in there, because sometimes they might assume the simple ones from the table. So I would have them logged, and I would have them with a nice descriptive nature, because clearly we have two solid cylinder examples. So one of them is rotating about its axis like this, right? Literally rotating, while the other one is rotating about an axis perpendicular, the way Max kind of spins his pencil like that. That's rotating about an axis perpendicular to the actual Apple Pencil like that, as opposed to like this. So being able to differentiate in your calculator, know which is which. So what's the ICOM for a solid, a solid cylinder about an axis perpendicular to the length of the cylinder? What is the ICOM for that? I don't have the table up, that's why I'm asking you guys to help me out here. Thank you. And what we'll notice, again, and I mentioned this last class, is that there's always going to be a distance squared in all these problems. It's going to be a mass times a distance squared. And that's what gives me the value for I. And that's what also gives me the units for I later on. And then finally, at the end, what do we have to put in? We have to put plus mh squared. And why are we putting the plus mh squared there? Because it's not an axis down the center of mass, but again, instead of the axis being here, the axis is over here. So whenever the axis we're rotating is parallel to your normal axis that you would use for the center of mass, we have to account for that gap. And that gap of 2.3 is going to go in here for each. So at this point, now it's just plug in. So most of the work for this problem is recognizing what's physically happening. The math is very simple for these problems. And what you're going to see is, as we go through the rest of Chapter 10 and Chapter 11, which, by the way, are our last two chapters we have to do, we're going to see more and more problems with rotation and see how they're really not any more difficult than F equals ma. Except now we're going to use torque instead of force. And instead of mass, we're going to use capital I for moment of inertia. And instead of A, we're going to use alpha. So these problems are very similar in nature. It's the setup that's the hardest part. So when we're practicing these, make sure you understand the setup, and now we can just plug in at this point. Does anyone have a number that they want to just share if others did their work ahead and want to check it? I'll start plugging in so you can see where things go. But at this point, it should be rather straightforward because everything is given in the problem. Thank you, Chris. This is 2.3 squared. And what are my units for I? Jazz, anywhere is fine. You can leave it over here, up there, down there. You're on mute, you're fine. I'm muted for a sec. Yes, kilogram meters squared, that's right. Because we have kilogram for mass, and then a meter times a meter. Kilogram meters squared. And there's not going to be a unit that we're going to use separate from that. We're not going to have a simplified unit for this. What does the number turn out to be? Anyone got a number for me? I'm going to take Chip's word. That sounds great, Chip. Thank you. 25.6 25.6 kilogram meters squared. So the idea in these problems is that, one, you're going to most likely have to calculate an I if it's away from its normal rotating axis using the parallel axis theorem. And that's probably the one thing when it comes to calculating I that you have to be able to do on this exam, is calculate an object's rotational inertia when it's not rotating about its center of mass. When it's rotating about its center of mass, either you are yourself going to calculate and derive it if it's simple, like we did with the thin rod, or they're going to give you the formula for that about its center of mass, or it's one of the ones from the table that we have already that you don't have to worry about. Any questions so far on this part for calculating I using the parallel axis theorem? Okay, I'm going to go on to the second one, so let's go to the next problem now. Okay, so we've got, let's see, determine the rotational inertia of the system and the angular speed if it is rotating with 150 joules of energy. Lengths are given in centimeters, by the way. I kind of just jotted that at the top there so you can see that. So we're given an object that's rotating about an axis. That axis, do you see the axis there? If you see an axis with a dot or an X, what does that mean about the axis? If you have a dot or an X, either one technically works for this. Good, and which way is the axis pointing? What phrase might you use? Good, outward or towards you, good. You could say out of the page, into the page. Those phrases are commonly used. And if you recall back from very beginning of this year when we did like cross products and dot products, we talked about how it can be out of the page, like the z-axis, or into the page, depending on which way you're looking. So that axis listed there, that dot, is an axis into the page. So this thing is rotating either in a counterclockwise fashion or in a clockwise fashion. But either way, we know that this thing is going to rotate like that around the axis. Does that make sense? So you can physically see the beginning of the problem now? Now, the next part is to recognize that we've got a couple things here. We're not given any information, any at all, about those segments connecting the masses, right? So in a problem like this, what is the assumption about those segments connecting the masses? What is the assumption that will be made? Go ahead, Max, yeah. Yeah, and that's interesting because obviously they're not because they're there. But the assumption is that the masses at those concentrated locations are so much greater than the masses of the rods connecting them that the masses of the rods have no effect. So you're going to see problems, and in the next one we're going to see one that it does have an effect. I'm trying to vary it for you here, where the rod connecting it may not play a role. So in this problem we have 4 masses, and if you think back, the original definition of I, what was the original definition of I? It was a summation. What was it the summation of? Before we did integration, before we got into the main formulas for the table, I talked about a definition of I as the summation of something. Can anyone recall what it was? Yeah. So it's the summation of mi ri squared. Very good. So if we think about this, what we're doing is we're looking at mr squared for 4 masses. That's all this problem is really doing with us. 4 masses, each with their own r value, each with their own m value. And we're going to get the m times r squared value for each of these and then sum them together. So in this problem, it's going to be m1 r1 squared plus m2 r2 squared, etc. And I'm going to do this just 4 times. Now remember, the r value is the distance from the rotating axis to that mass. The rotating axis to that mass. We'll take a break in about 3 minutes. And that's again the r value. It's not the gap from mass to mass. So we have to consider that fact as we're going through this problem. So let me go ahead and zoom out a little bit. Alright, so let's see what we've got here. We've got the I value equal to the first mass, which is m1, is 2. Its distance is 2 centimeters away, so can I use a 2 there? I can, as long as I recognize that my units are going to be kilograms centimeters squared in the end. So if you don't want to change your units right now, and you're not doing anything with this I value, you can leave it. Now, I'm going to let you know that based on the second part of this problem, it gives us a certain amount of kinetic energy or energy. We're going to probably want standard units, right? So although I was saying, you don't really need to change the units as long as you write centimeters squared, for this problem, I would change the units. I would write this as 0.02 meters. And again, that's this right here. Right, this is really 0.02 meters because it's given in centimeters. The next one, we look at the second mass. And the second mass is 1 kilogram times its distance from the central axis, which is 4 centimeters. What am I referring to? I'm going from here all the way to the second mass. So this is the 4 centimeter distance right there. So this is going to be 0.04 squared. The third mass is 5 kilograms times its distance, which is going to be, what is that going to be? 0.055, 0.055 squared, plus the final one, which is going to be 3.1 kilos times 0.065 squared. Okay, so again, where am I getting the R values? It's the distance from the rotating axis to the actual mass itself. So this problem, we're looking at concentrated masses. We're not looking at objects that have some length or radius to them, and that object is spinning about its own axis or some parallel axis. It's just objects themselves or masses. This is kind of like the video we watched the other day, if you recall, when we were in class. We watched that video with the guy flipping physics, if you recall, and he like had the 3 or 4 different masses that were rotating about, and one of them was further in, one was further out. That's kind of what we're looking at in our problem here. All right, so what do we get for an I value for this? Can somebody give me a value, please? All right, I'm going to assume that these calculations are right for now. If they're not, somebody else chime in and let me know that they got something different if they did. It was a 225. I'll also throw another 3 in there just for the sake of it. A very small number because why? Our distances were very small, and those are squared, so we can expect a very small value here. Now, how about the second part? So we did the first part, determine the rotational inertia, right? That's done. And then it says, if the angular speed, of the system and the angular speed, we're determining that, if it's rotating with 150 joules of energy. So if it's rotating with that energy, what kind of energy is that? If it's rotating, it's got to be kinetic because of the motion involved. Good. The other option obviously is potential, right? Or potential elastic, where it's like a spring that's storing energy and then the rotating thing is going to start rotating afterward. Like a wind-up toy when you twist it and then let it go and it starts spinning. But in this problem, it is rotating. There's nothing about gravitational potential energy at all. So that is the kinetic energy that's given. So for the second part of this problem, what we have to now do is recognize that we're given the kinetic energy of 150, and we know the formula for kinetic energy, and this is rotational kinetic energy. It's 1/2 I omega squared. And how did I know that right away? I didn't memorize that, guys, at all. I just took the old kinetic energy formula and plugged in I for m, and I plugged in omega for velocity or speed. So we're looking at the angular speed and the rotational inertia instead of the mass and the normal speed for kinetic energy. And then at this point we have everything, right? We're trying to solve for omega. So let's multiply by 2, divide by I, and square root it to get omega by itself. So the K value is 150, and the I value is 0.03063. So there's our omega value for this problem. You're going to notice that on the AP exam, they're not going to simply ask you for the I value at times. It's going to be related to other things. So I is probably never going to be a standalone problem, unless it's a multiple choice. But again, do we have multiple choice now? We do not. So what I've done is I've pushed myself to really push us in this next quarter to not even really consider multiple choice anymore because it's kind of been dropped from the exam, which I know, right? We'll talk about that after the break. Take a 2-minute break, and then I'll tell you more about that. Get up, walk around for a little bit. I'm going to do the same thing myself. I'm physically going to get up and walk just so I can stretch my legs as well. And feel free to mute yourself or turn the camera off for a minute. And come back in 2 minutes, please. So the third problem says the following. In the figure, D1 is 2.3 meters, D2 is 1.8 meter, and the mass given is 1.3 kilograms, and the mass of the rod is 5 kilograms. Determine the rotational inertia of the system. So, this is a combined problem. This is the one I was saying before. So the previous problem, two problems ago, we looked at a rod rotating, or a solid cylinder rotating, and using the parallel axis theorem. Now, in this problem, we have to consider this. First, where is this rod rotating about? Its center of mass or not center of mass? Answer that question first. Yeah, it's not the center of mass that it's rotating. The center of mass in this problem is right here. And the idea is that it has to be in this problem, the center of mass of this in the center, because it's uniform, but it's not. It's rotating here. So this is a problem where this rod is rotating about an axis that's not its center of mass. So right away, we're going to have to use the parallel axis theorem for the rod. But then we've also got this concentrated mass that's rotating as well. So either it's rotating like this, right, in a counterclockwise fashion, or like this, in a clockwise fashion. So for this problem, what we have to do is we have to consider we have two parts. We've got the rod rotating, not about its center of mass, so that's parallel axis, and then the mass rotating, that's concentrated. So let's start by writing this. So I is going to equal, let's say, I rod plus I mass. And maybe I'll just call that I2 actually for now. And I'll call that M2 for now to be consistent with subscripts. So the I of the rod, though, we have to consider, well, that is really, again, the I of the center of mass plus mh squared, and then again plus the second mass. So remember, this is the rod right here. That's what we're talking about right there. And it's rotating, again, about its end. And if you recall, we derived this formula about its end, and we did that, I think, a class ago now. And we came up with a formula we could use, but you know what, we don't have to come up with a formula for the moment of inertia about the end. We don't have to derive it because we have the parallel axis theorem. So the parallel axis theorem simplifies things for us, because if we didn't have it, we'd have to use integration and figure out that rotational inertia about the end like we did in class that day, but I don't want to do that. I'd rather say, you know what, let's just use the parallel axis theorem instead. So let's go ahead and do that. So let's think about what's going on here. First, we have to define some things. So this is a rod normally rotating about its center. So I'm going to redraw it. Okay, there's the rod. When I draw a rod, I'm going to draw a line for now. If I'm drawing a solid cylinder rotating about its center of mass, I'll draw what looks like a cylinder. And we know that its center of mass is down the middle if it's uniform. So that's normally the situation where this thing is rotating, right, about its center of mass like that. That's what's normally happening. But instead, it's rotating about an axis all the way over here. So again, my h value is going to be half of the length of the rod. Half of the length of the rod. And that length of the rod is given in the formula. So that's what the mh squared is going to play a role. Now, so I'll put the plus here, and this is going to be plus, and this is going to be, what's the length of the rod given as? D1, right? D1, I think, in the problem. So let's put D1 over 2, because that's what the distance is. Remember, this length here is D1 divided by 2. So that's going to go in for h, the distance between those two parallel axes that we just drew. The yellow and the black axes, I'm talking. Sorry, not yellow, the green and black axis. What is the center of mass of a thin rod about its center? And this is, again, I'm not asking you to memorize it, I'm just asking you guys to reference your table to practice. So go back to your table at least, either in your textbook. Yeah, we go. And in this problem, L is really D1. So I'm going to replace L squared with D1 squared. So again, Spencer wasn't doing anything. He was just literally looking at the table and saying, okay, which one of these is a fit? And we've got a thin rod rotating about its center. And I'm assuming Spencer is right. So if anyone disagrees, obviously chime in. Now the second part is to consider the mass that's concentrated at a distance d2. And that is going to simply be just like we did the previous problem. There we go. Like we did mr squared, this is going to be plus the mass of that concentrated object times the distance it is from the rotating axis squared. And that's going to be d2 squared. So the general formula, okay, again, the general formula here, if we think about it, this is 1/12 ml squared right here. This is plus mh squared, and this is mr squared, really. So if I want to write it on the side, I'll write down these formulas. This comes from mr squared. This is 1/12 ml squared. So those formulas in red, I've already substituted in for L as D1, and R as D2, and H as D1 divided by 2. So keep that in mind, that's where those formulas are coming from. I'm not just arbitrarily choosing like D1 divided by 2 here and D2 here. Those aren't just random spots that I'm choosing. They come from this formula here, because the R value is the distance from the rotating axis and the mass. This distance is D2, which is why this comes in as D2 here. And then again, the distance between the center of mass of the rod and the rotating axis is given as h, and that's half the length of the rod, which is why we're using d1 divided by 2 there for h. Any questions on this problem? And we can plug in numbers in a second, but any questions so far? Once you do one or two of these, it gets a lot easier. So last night, like my homework last night before this class was to practice, and I did about 8 or 10 of these problems at the end of the chapter, and then I modified them slightly to make them new problems for you guys to practice. But your homework problems you're going to get are going to be similar in nature. You're going to practice the same way. Some of them are going to give you things with kinetic energy, some will have rotational speed in them, some will just be I problems like this one is. So be able to, work with kinetic energy of rotation and I in the same problem, because K equals 1/2 I omega squared. So keep that in mind. All right, if there's no questions, can I get a number? Oh, go ahead. Yeah. That's the distance to the rotational axis. So it's the distance between, here, I'll put it on the figure. So, center. Great point there, Chris. You hear what Chris is asking about? Okay, we're measuring the distance from the center of that concentrated mass. Because that concentrated mass technically could have some width to it, but Chris, if it does, it becomes a sphere, and then we have a formula for that. So if you think back, that would be another parallel axis problem if that object, M2, had some, I don't want to use the word depth, but some three-dimensional dimension to it. M2 is considered to be an infinitesimally small mass concentrated at that exact location. But if it had any sort of radius, M2, then we have to look at a sphere, and that sphere would be at a distance parallel to its rotating axis, so it would be another parallel axis problem. Okay, that's a great question. Does everybody understand what Chris was asking there? If mass 2 had some size to it, if it was like a basketball, then you would have to use the sphere, and you would have to use the parallel axis theorem for the sphere now. And the sphere is on the table as well, if you go back in your notes and look at the table. Or go to the page. Anybody know the page off the top of their head? What reference number is it? So we all... Okay. So it's on the Moodle page as well, on the notes. If you want to look in your textbook, it's in there as well. So 274, perfect. Okay, so page 274 in the textbook, or slide 34 on the chapter 10 notes that Spencer's referring to on Moodle. All right, we'd plug in numbers at this point. All right, 1/12. Now this mass is the mass of the rod, remember in the beginning here first? So the mass of the rod is 5 kilograms, and then D1 was given as 2.3 meters. And I don't need those parentheses actually anymore, right? Because I'm just adding everything. I just used the parentheses earlier to separate them so you guys can see them. The mass that's concentrated is 1.3, and its distance from the rotating axis is D2, which is 1.8. And That's squared. So remember, if you forget your squared term, it's like you're forgetting the fact that it's mr squared or ml squared. So keep that in mind as you're doing these problems. Did anyone get a number for this already? 13? Okay. Any questions at all on this one? Again, the number plugging in is not as important. If you're getting the wrong answer there, just go back in your calculator and practice again. But it's more the theory that I want to ask questions about. Okay. All right, so here's what I'd like to do. Let's see, class will go till almost 9:40, so we only have about 3 minutes left. So let me talk about what we're going to start in the next class. I'm going to give you guys about a 10-minute break before your next class. If you want to hang back and ask questions or ask me anything or go over 10-5 more problems together, I'm happy to continue for the next 10-15 minutes for anyone who wants to hang out. But I'm going to give you that opportunity to give yourself a little mental refresh. But let me give you an overview of what we're going to do in the next class. So I want to cover 10.6, 10.7, and 10.8 as one section. And the reasoning is that it's literally the same as translational motion, but now we're just getting new equations. And because of the fact that you guys are going to have access to a full equation sheet in addition to whatever you want to write in another equation sheet, this will make this even easier for this topic. So when we get to F equals ma in linear things, now it becomes, again, torque equals I times omega. And we'll talk about torque in the next section as well. And then torque is really just force times distance, which is kind of similar to work. So we're going to see how there's a lot of analogous nature in the next couple of things, and then we'll start talking about things that are rotating. We'll look more at the problems of those. So next class, I'm going to go over the theory of 10.6, 10.7, 10.8, and try to start 1 or 2 practice problems in that class. So my recommendation, besides doing your normal homework like you do already, is maybe just read through 10, 6, 7, and 8 before the next class. I think a lot of you will start realizing that it does help to read the text before the class. So if you want something to give yourself a little bit of, a nice little, a little review of torque from last year, like you should have seen torque last year. Just remind me, did you guys see the concept of torque at some point? Okay. I don't know how far in depth you went with it, and we'll talk about rotational equilibrium and stuff, and we'll start that like as if we don't know it, but torque should be familiar to you. And then after that, it's just taking equations that we have already and manipulating them into like slightly different equations that we're going to be looking at. That's kind of where we're at. So let me just quickly look at the Moodle page. I want to make sure that I'm not forgetting anything that I put up there. So just to overview what we have coming up, you guys have the 10.5 homework that's now been assigned. So I would recommend starting that one because we finished it today. Let's see. Yeah, so 10.5 I assigned, and I made that due on April 2nd, which is going to be on Thursday when I meet with you guys. And then on Friday, you're going to have your second Ed Puzzle video due. And then 10.6 to 10.8, my hope is going to be to finish that or to cover that next class, but that may not happen. So I put to be determined right now. That date might change. And then the third Ed Puzzle video is going to be a review video from kinematics from earlier this year. I'm going to start putting Ed Puzzle videos up that are kind of reviews from each topic that we've covered throughout the year. Any questions where we're at right now? I think 2 of you owe me labs still. You know who you are. I sent you guys emails, so if you owe me lab 11, I would recommend getting that ASAP. Big part of your third quarter grade. You only have 3-4 labs, I think, this quarter. So if you're missing 1 lab, 25%, labs are worth 20, 30%. That's 7.5 points on your GPA, or on your quarter grade. So it's kind of a big deal. So definitely get me that lab. And that one, if you remember, all you have to do is use the passcode to fill in the stuff that's there. So you don't have to do an entire lab write-up for that. And a lot of you did that already. It's just using the passcode setup in the third arrangement where it's whatever, student guided or whatever they call that. Okay, with that said, feel free to go. You guys have about 10 minutes before your next class starts. If you want to hang back and ask questions or do some more problems, feel free to hang back. Oh, good question, actually. You're welcome, guys. M, that's a great question about TA. I talked to Spence about this for CAD yesterday for a while, actually. So for TA, see you later, Chris. For TA for honors, here's what I'm thinking. So first, so you're not responsible for going to gym now, so that's not a conflict at this point? Okay, so like we did, oops.